Now, let's look at basically the characteristics associated with active power and frequency of a synchronous generator. So here we're showing two diagrams, which are kind of similar to one another. The first one is showing the mechanical speed, and this is showing the frequency. So these two are proportional, as we know, in a synchronous generator. And on the horizontal axis, we have the power that is delivered by the generator. So let's focus on this second one, because this first one is kind of similar to the second one, and we're going to discuss on the second curve here. When there is no power delivered by the generator, or P is equal to 0, our generator's frequency is at FNL, where NL is standing for no load. So F of NL means the frequency under no load conditions. Okay? Now, under full load conditions, we are delivering this much of power from the generator, and the frequency of the machine usually drops to be at FL, the frequency at full load conditions. So the operation of generators is usually like that. We want our generators to obey this curve between the no load and full load conditions. We want them to basically work based on this droop line. This is what we call the droop line, where this droop slope is typically around 2 to 4%, and it's negative by nature, which means that if you deliver more power, then the frequency will drop. So pay attention to these conditions: no load, full load, and partial load. Partial load means something in between 0 and full load. So somewhere around here, we are always operating our generator between the no load and full load conditions, right? We want to be corresponding based off of this line, which means that the frequency should be obeying based on this droop line. So based on this, the slope of the droop characteristic would be coming from this line, P full load over F no load minus F full load, right? So this is coming from this line, nothing special. So based on this line, under partial load conditions, the relationship between the frequency and power under partial load conditions can come from this SP and F at no load conditions. So this is just coming from this line. This is nothing special. We can use this equation to come up with the frequency or power at partial load conditions, whichever is unknown to us, based on the problem statement that we are encountered with. So keep that in mind. The same type of basically relationship also can exist between reactive power and voltage. So remember, always frequency is corresponding with active power, and a voltage is corresponding with reactive power in synchronous generators. So here is a relationship between the voltage in the terminal and the reactive power. And also keep that in mind. This basically line, the frequency versus active power relationship, can be governed through your governor system, which is attached to the mechanical motion, mechanical side, or mechanical power in your generator. However, this relationship between the voltage and reactive power is coming from the excitation system. Okay, so there are two different systems: the excitation system, which is working with respect to the voltage and reactive power, and your governor system, which is working based off of the active power and frequency. Keep that in mind. So same type of relationship can exist between or will exist between the terminal voltage and the reactive power delivered. Here is reactive power is 0 when we are under no load. This VT under no load would be this much. When we are providing the full reactive power, then VT terminal voltage at full load condition would be this. And when we connect these two, we get a line which has a certain slope. That slope comes from this equation. And this is going to be the relationship between basically this line and the Q delivered at partial load with respect to the voltage in terminal at partial load conditions. Okay. Now, let's go to this problem. Example 5.5. We're having basically one generator that is providing load 1, and a second load is going to be connected to this system. So a generator is supplying a load 1. A second load is to be connected in parallel with the first one. The generator has a no load frequency of 61 Hertz and a slope of SP, which we defined it here, 1 megawatt per Hertz. Load 1 is consuming a real power of 1,000 kilowatt at 0.8 lagging power factor, while load 2 is consuming a real power of 800 kilowatt at 0.707 power factor lag. Now, before the switch is closed, what is the operating frequency of the system? So part A, when the system is basically using this characteristic, when there is only one load in the system, you can come up with F of the system, or F at basically loaded conditions, to be equal to F at no load conditions minus this P over SP. P is 1,000 kilowatts, which gives us a 60 hertz. After load 2 is connected, then we're adding to the load by 800 megawatts. So this makes our basically frequency to go less than 60 hertz to become at 59.2. Now, part C is asking, how can we correct this frequency to go back to 60 hertz? That will need to be done into using basically the governor system. So to restore the system to its proper operating frequency, the operator should increase the governor no load set point by 0.8 hertz. So if you make this 61.8 instead of 61, make the FNL at 61.8 hertz, then it can bring the system back to 60 hertz. So that's the action that is going to be done by the governor system, which in practice means that you need to provide more mechanical power on the mechanical side because you need to provide more load, right? As you're growing the load on the electric side, the frequency drops. To bring the frequency back to where it should be, you need to push more mechanical power to correct the frequency. All right, now when we are operating basically parallel systems, parallel generators, and if you want to bring a new generator to the system, it's as if you're having a large pool, which you call it an infinite bus. An infinite bus means that we have basically a power system so large that its voltage and frequency doesn't change despite how much active power you're giving or taking from the system. The frequency is remaining constant. Same thing about reactive power. It doesn't matter how much reactive power you're giving or taking from the system, the terminal voltage will remain constant in an infinite bus. Okay. Now, in order to parallel a system with this infinite bus, we can look at this scenario. This is an infinite bus, which is providing some loads, and you're going to bring another generator to the system, to this system of infinite bus. This infinite bus internally means a few thousand generators, for example. And you're going to bring another generator in circuit with the rest. Then, based on the characteristics of this infinite bus and your generator, you can come up with a visual, basically representation of how much the share of the new generator should be, how much this new generator should share this load. So this load is, for example, 1,000 megawatts. You might come up with a case that 950 megawatts is coming from this side, the infinite bus, and another 50 megawatt will have to come from the upcoming generator. And this is showing that case. You can put those two characteristics. And then, of course, you want the frequency to be the same as the infinite bus frequency. So that dictates how much power needs to be coming from your new generator, how much would be the share of your new generator in the system. Here is an example that shows that concept. We have two generators which are supplying a load. Generator 1 has a no-load frequency of 61.5 hertz, slope SP1 equal to 1 megawatt per hertz. Generator number 2 has a no-load frequency of 61 hertz, slope of SP2 equal to 1 megawatt per hertz. These two generators are supplying a real load totaling 2.5 megawatts at 0.8 power factor lagging. At what frequency is the system operating? How much power is supplied by each generator? So we're talking about the share of power between two generators. We know that the two loads, P1 plus P2, should be equal to the total 2.5. Now, P1 would be corresponding to this equation. P2 would be corresponding to this equation. Since Fsys should be the same, and F no load between the two generators would be also two different numbers in general, you can come up with basically the solution to F of the system, which comes out at 60 hertz. Now, plugging this 60 hertz back into each individual basically statements, you can find out that P1 is 1.5 megawatts, P2 is 1 megawatt. So each generator has been sharing a certain amount of the total load. Now, in part B, we're going to add an additional 1 megawatt load. So when you're adding 1 megawatt load, total load would be 3.5 megawatts, and your frequency will drop to 59.5 hertz, which means that each generator is now giving 2 megawatt and 1.5 megawatt. but the frequency of the system is 59.5. Now in part C, it's asking, with the system in the configuration, what will the system frequency and generator powers be if the governor set point on generator 2 is increased by 0.5 hertz? So we're going to change basically generator 2 from 61 to 61.5, its no load frequency through the governor system. So that will increase basically the F to 59.75 hertz. So we can increase the frequency from 59.5 using the governor system in generator number 2 to 59.75 hertz. Now you can get an idea of how you can correct the frequency back to 60 hertz by changing, for example, this no load frequency of generator 1 or 2, or them combined together, for example, how this can correct the total frequency of the system back. And the resulting power would be, because of this action, would be that both generators will share the same amount of load, 1.75. So each generator would be responsible for providing half of the load because of this action. When we're talking about the capability curve, we're talking about the area or the region in which your generator can operate in terms of active and reactive powers. How much active power it can deliver safely, how much reactive power it can deliver safely at the same time. So this would be associated with a curve of P on the horizontal axis versus Q on the vertical axis. And I'm just explaining this curve, and I'll explain how this curve can be found. So in this curve, there are multiple, in this basically capability curve, there are multiple curves that have been intersected with one another. And you should really consider the region that is between all of those curves. So this is telling you that there is a limit on the Q that your generator can deliver. This basically circle also tells you that there is some kind of limitation associated with your generator that is in general associated with the S, or the apparent power. So each of the points on this circle are showing 1P and 1Q, right? If you go here, there's 1P and 1Q. So overall, you should be always under the areas that have been intersected with these. So this is a good operating point. This is a good operating point. This is a good operating point, but this is not a good operating point because it goes beyond those curves. This is not a good operating point, although it is satisfying this circle, but does not satisfy this one, right? So it's beyond that. So therefore, you should always care about being under those curves collectively. So in general, we're explaining the safe region of active and reactive power generations. We're assuming that for that, in order to find that curve, we will be assuming that V phi is constant. V phi is the representation of the terminal voltage. From the rated conditions, V phi is constant. We're assuming that we are working on the rated voltage conditions. So the rated S, the rated apparent power that the generator can deliver would be 3 times V phi IA, because we have a 3-phase system. So 3 times V phi IA should give you the S. So this can give you basically this 3 V phi is constant. This relationship between S and IA can give you or determine the limit for IA, or the stator current limit. And this is nothing but this circle. So this is a circle. This is a circle that you can see that is associated with a center of 0 and a radius of 3 times V phi IA. And this S is your apparent power, rated apparent power of your generator. This is coming from the ratings, right? So if you have a 100 MVA generator, this S should be 100 MVA. If the rated voltage on your generator is 20 kilovolt, this V phi should be 20 kilovolt. And this will determine this circle for you. Is that clear? So this is coming from there. Also keep that in mind that EA, the internal voltage or the armature voltage of your machine, is equal to K phi omega. Remember, this K was a constant. Phi was basically associated with the flux per pole, and omega was the speed of the machine. So if you're assuming that omega is at the rated omega, omega is constant because you have a synchronous generator, right? Then you can relate basically the limit for Q through this, because you know that in order to change Q, you should change EA, right? If you're assuming that omega is constant, then EA is the armature voltage, phi, and Q would be interconnected with one another. Okay. Now, how you find basically this curve through this is through a scaling factor, this curve. So this is how it can be explained. This is the phasor diagram. V phi plus JXSIA would be equal to EA. So this is coming from the equivalent circuit of your generator. This was the equivalent circuit of your generator, if you recall, for each phase. So we had an RA and JXS. If you ignore RA, then EA would be related to V phi through the current and XS. So that's how this phasor diagram has been constructed. Now, if you use a scale factor of 3 times V phi over XS, meaning that this V phi becomes V phi times 3 phi over XS, this length instead of basically XA IA is getting multiplied by this, and this is also getting multiplied. So if you're just using that scaling factor, that gives you a length here that is equal to 3 times EA V phi over XS. Now, this curve is found from a circle having a center of minus 3 V phi squared over XS, which is associated with this length, and a radius of this much, 3 times EA V phi over XS. So this length is equal to DE, and the center with respect to this origin point is minus 3 V phi squared over XS. So keep that in mind. These are all basically constant numbers. So this can give you this curve. So using that, this capability curve can be found. There is another region that we might consider into this capability curve, and that's associated with the maximum power that you can push from the prime mover on the mechanical side. So on the mechanical side, you may not be able to push more than this power that is shown with this straight line. So you can see that you are making your capability curve even stricter with respect to what you had in here. So this now becomes the area under which you should operate. You're limited by another factor in here, which is the prime mover power limit. We have a 480 volt, 50 hertz, Y-connected 6-pole synchronous generator rated at 50 kVA at 0.8 lagging power factor. The synchronous reactance is 1 ohm per phase. Assume that the generator is connected to a steam turbine capable of supplying up to 45 kilowatts. The friction and windage losses are 1.5 kilowatt, and the core losses are 1 kilowatt. We want to sketch the capability curve for this generator, including the prime mover power limit. Okay, so for that, first of all, we should talk about this circle. The circle is coming from this curve. S rated is equal to 3 times V phi rated times IA max. So V phi is coming from the terminal voltage divided by square root of 3. This 480 volts is the terminal voltage. Since we are Y-connected, V phi can be found from 480 over a SQRT of 3. So V phi would be 277 volts. Okay? So this is V phi. And the maximum current would be S rated. What is S rated? S rated is 50 kVA. This is coming from the rating of the machine. So IA max would be 60 amps. Now, with this information, we're going to draw the capability curve. So the maximum permissible apparent power is 50 kVA, which specifies the maximum safe armature current. And the center of EA would be minus 3 V phi squared over XS. So V phi is coming from here. XS is given to us at here. So this gives us the center point at minus 230 kilovars. So this is minus 230 kilovars. If you go down, this is the origin of the maximum rotor current. The maximum size of EA is given by, so we find EA is V phi plus JXS IA. This IA would be your IA max. And we're working under what conditions? 0.8 power factor lagging. So this gives us the EA. We're going to assume that this EA is the maximum EA because it's been found from the rated conditions of your machine. Therefore, you find that DE magnitude, the DE magnitude, 3 times VA over V phi over XS. So this basically gives you 263. So we found the origin point, the center, minus 230. And its radius is 263. So from here, we are going to have a circle which goes up to this point. That point is, so this is 263. This is minus 230. Minus 230 plus 263, that becomes how much? This is 33. Now, you have another restriction, and that's the maximum power by the prime mover is 45 kilowatts. You have some basically losses in the machine. So you need to consider those losses, which are 1.5 kilowatt and 1 kilowatt. You need to subtract those. So this is really 42.5. So this P max is 42.5 megawatts. That's because 45 is given by the generator on the mechanical side, but this capability curve is associated with the electric side of the machine. So you have to subtract those basically losses on the machine also. So this S rated is how much? 50 kVA. So you go from this circle, this smaller circle, would be associated with this 50 kVA. So when 50 kVA goes on the horizontal axis, that becomes 50 kilowatts. So this is a circle, this small circle is a circle of the origin point, 0, with 50 as its radius. So this is the smaller circle. This is the bigger circle, which is associated with the center of minus 230 and a radius of 263. And finally, this is basically your straight line, which is coming from here, 42.5 kilowatts. Part B. We're asking, can this generator supply a line current of 55 amps at 0.7 power factor lagging? Why or why not? So you really need to basically consider that 56 amps at 0.7 power factor lagging to be associated with what P? So this is the P, 3 times V phi IA cosine of theta. And the reactive power is 3 times V phi IA sine theta. So it gives you a point of 32.6 and 33.2. If you go to your capability curve, so plotting this point on the capability diagram shows that it is safely within the maximum IA curve, but outside the
max IF curve.
What is the maximum amount of reactive power this generator can produce? So the maximum reactive power is really this point, right? Which is coming from 263 minus 230. This 263 is this basically length. And this 230 is associated with the origin point. So when you basically add them together, that gives you the 33 kilovars. So this point is the maximum power, reactive power, that is 33 kilovars. In part D, if the generator supplies 30 kilowatt of real power, what is the maximum amount of reactive power? So you have to go 30 kilowatt and go up. And wherever you are intersecting with each of these two, that would be the answer. If the generator is supplying 30 kilowatt, the maximum reactive power is 31.5. So you have to go up from 30 all the way up to see the reactive power. Now the limiting factor in this case is the field current. The armature will be safe up to 39.8 kilovars. So this is the field current and this is the armature.